All right. Okay, so can everyone see the screen that I'm sharing?
Yes.
Okay, cool.
Yeah.
Okay, awesome. So, all right, so all of you who are here, welcome to MCAT 101 topic session on organic chemistry techniques. Today we're going to focus on separation and purification techniques. So how basically it's going to work is I have the first half of the presentation. Ashley is going to be doing the second half. And my usual policy is if you have any questions, you can feel free to put it in the chat, interrupt if you need to, and then I'll get to your question as soon as possible. That way you can ask your questions in the context that you have them and that you don't forget, and we're able to address it right away. So we can make sure we're all on the same page. And one thing I always say at the beginning of all my sessions is the only stupid question is the one that you have but don't ask. So this is a non-judgmental space, no one's going to think less of you for asking a perfectly valid question. So Ashley, do you have anything you want to add?
Please participate. We have lots of questions lined up for you. And if you are feeling confident in your answer, please feel free to jump in and just explain how you got it.
Yeah, and if you're not confident, take a stab at it. There are no points here. I'm not grading you and no one else is. So, all right, so we can get started, and I'll be kind of monitoring the chat. A couple of the other tutors like Kwan and Sim are going to be monitoring the chat as well, and we'll be able to hopefully address all of your questions. Okay, awesome. So let's get started. Okay, so the topics we're going to cover, that I'm going to cover, are extraction and distillation, and Ashley is going to cover chromatography. So I guess before we talk about extraction, I would say when it comes to knowing these techniques, the key is to know when you might use them and how they work and what the results might look like. You don't always have to know the exact mechanisms of what's happening, especially with something like fractional distillation, and we'll get to all of those. And it's really important that you can quickly recognize when a given technique is relevant or why it might be used. And just keep that in mind if you feel overwhelmed by a particular experimental protocol in a passage. So let's start with extraction. So extraction is essentially based on the idea that we're going to isolate a desired compound or separate two compounds based on them having different levels of solubility in polar versus non-polar solvents. So those of you who've taken organic chemistry have probably done this at some point. And this usually involves two layers: an organic layer with a non-polar solvent like diethyl ether, where hydrophobic compounds like to hang out, so long hydrocarbon chains, neutral or non-polar molecules, lipids, etc. And an aqueous layer that's usually having a polar solvent, typically water, where hydrophilic compounds like to hang out, like charged molecules, ions, short carbon chains that have a polar functional group, etc. And the basic principle here is that like dissolves like. And one thing to note that becomes really useful is that if you add a charge to a non-polar molecule, it's likely to migrate to the aqueous layer where that charge can be solvated by water. So let's look at a basic example here. So let's say that we ran a lipolysis reaction, which is a fancy way of saying you take a triglyceride and you break it down into fatty acids and glycerol. So we're looking at an aqueous layer that contains glycerol and fatty acid salts. So that's going to be the ionic form of the carboxylic acid group on the fatty acid. And R in this case is just a long carbon chain of 10 or more carbons. So Both of these are going to be sitting in the aqueous layer because one of them is very polar. The other one has a long nonpolar tail, but is still charged. So they both sit in the aqueous layer. And we want to isolate each component separately. So the first thing we might notice is that we have an acidic group. It's been deprotonated, and that's why it's negatively charged. So the first thing we can do is we can add some dilute hydrochloric acid. Now, what that's going to do is that's going to reprotonate the carboxylic acid group on the fatty acid, which then now makes it neutral. And because of that long carbon chain, it's going to be neutral and nonpolar. Okay, question, are all acidic groups negatively charged? So usually, yes. I mean, like acidic groups like COOH. COOH is the one you're going to see a lot because that's like one of the few organic acidic groups. So typically you're going to see acidic groups being negatively charged because you're releasing a proton and keeping a lone pair. If any of y'all can think of an example where that doesn't apply, go ahead and put it in the chat and we can talk about it. But for the most part, yes, they're negatively charged when they're deprotonated. Okay, so we protonate the carboxylate and leave the glycerol unaffected because it's not acidically or basically active. So that gives us. So then now we have an acidic aqueous layer, and we have protonated carboxylic acid, fatty acid, and glycerol. Now the next thing we can do is we can add hexane, which will create an organic layer in the beaker. And then if we mix the two layers by shaking it or stirring it so that there's turnover, we now find that the fatty acid is going to be in the organic layer. And since a separatory funnel, which we'll get to in a moment, can open from the bottom, you can actually just drain out the bottom layer and leave the organic layer behind. And so then we have our pure fatty acid in the organic layer. But now we have glycerol floating in a bunch of acid. So to deal with that, to isolate the glycerol, we can neutralize the acid in the solution using dilute base. So then we'll end up with a neutral solution, a neutral aqueous solution containing glycerol, and in a neutral organic solution containing the fatty acid. So does that make sense?
Yeah.
Okay. All right. Yeah. Quantum makes a good point. Like if you have like a protonated amine group, so like an NH3+ group, that's going to act as an acid. But typically like molecules in their default neutral state that are acids. How come the carboxylic acid? Okay, that's a good question. So let's go back a moment. Now, remember how I said that R is actually a 10 or more carbon chain. So yes, it is it does have a polar group, but because the hydrocarbon tail of the fatty acid is so long, polarity won't cut it as far as making it soluble in an aqueous solution. So if we go back a few slides, go back here, see how a charged molecule, no matter how long it is, will end up in the aqueous group because a full charge is a big deal as far as being soluble in a polar solvent. But yes, so a short carbon chain, like 5 or less, with a polar functional group will be soluble in water. But if the carbon chain is longer than 5, only a full charge will actually allow it to be soluble in an aqueous layer. Okay, excellent. So if there are no further questions, we can keep going. If you think of a question about this, we can always come back to it. Okay, so extraction, basic things to remember. 2 very important things. One, the bottom layer is not always the aqueous layer. You're going to see, you might see an example in a passage where they use a polar solvent that's actually less dense than the non-polar solvent. So always look at what solvent you're using. Never assume that the top layer or the bottom layer is a certain one of the layers. Always check. And then extraction often takes place in a separatory funnel. So essentially, I don't know if you can see this, but this is how you can drain that bottom layer by opening that valve. And can everyone see it?
Yeah.
Can people see it? Okay, yeah. So you're going to drain that liquid, and that's essentially how extraction usually works. As far as the MCAT goes, that first tip is going to be more important than the second, but it's good to know. Okay, let's do a short question. So which of the following compounds, so for each compound, will it dissolve in an aqueous solvent or an organic solvent? So I'll give you a second to think about it. You can answer in the chat, like 1, 2, and 3. What do you think? Okay, I'll give you guys a few more seconds to put in your vote. Okay, yeah, good. Okay, yeah. So let's quick go through it. Seems like y'all are getting it. Ethanol, short carbon chain with a polar group, aqueous. Hexane is a nonpolar hydrocarbon chain, no polar groups. So it's going to be in the organic layer. And then glucose, it has 6 carbons, but a ton of polar groups. Therefore, that is enough to overcome the non-polarity of the carbons and the CH bonds, and therefore we have glucose in the aqueous layer. Okay. So some basic kind of patterns you might see in extraction. So extraction of basic compounds. Basic compounds, especially organic molecules with an amine group, NH2, can be extracted from organic solutions by adding a dilute but strong acid. And that protonates the basic group, giving it a positive charge. And now the base is going to be soluble in the aqueous layer and will no longer be in the organic layer. So here's an example. You have your amine, you add some acid, you protonate it, it migrates to the aqueous layer. Now, acidic compounds specifically carboxylic acid can be extracted using a dilute weak or strong base. And so the COH group is deprotonated, giving it a negative charge, and then the carboxylic acid goes from being soluble in the organic layer to being much more soluble in the aqueous layer. And you can see that here. It goes from organic to aqueous with the addition of base. Okay, phenol. So phenol, the extraction of phenol is very similar to the carboxylic acid, but it requires a strong base. A strong base will deprotonate the OH group, giving the molecule a negative charge and making it more soluble in water. So it seems pretty, yeah. So it's going to go from the organic layer to the aqueous layer. So now let's look at a more complicated example. So let's say we've got an organic solution with diethyl ether being the solvent, and we've got 4 organic molecules: naphthalene, P-cresol, benzoic acid, and aniline. So we want to extract the naphthalene and save the other molecules separately for later. Now, if we do a quick survey of our molecules, we can see that we've got an aromatic non-polar molecule, naphthalene, that's neutral. Yeah, addressing the question in the chat, yes. If there are an equal number of there's an equal number of C's and OHs, yeah, because the sheer number of OHs is going to kind of tip the scales in the favor of aqueous solubility. Okay, so naphthalene, non-polar, non-acidic, non-basic. P-cresol is going to be a very weak acid. Benzoic acid is going to be a pretty decent acid, so we can consider that acidic. And then aniline is a decently basic molecule. So we've got an acid, a base, a very weak acid, and then a neutral molecule. So the order of the steps isn't super important, but let's say they want to get rid of the benzoic acid first. So the first thing we can do is, since it's a pretty decent acid, we can use a weak base. Now, if we use a strong base, that's going to deprotonate both the benzoic acid and the P-cresol, but we only want to get one molecule at a time. So we can begin with a weak base. What that's going to do is that's going to deprotonate. Yeah, we add a weak base like bicarbonate, and it's going to deprotonate the benzoic acid and only the benzoic acid, and that's going to convert it to benzoate, which is ionic, or which has a charge, and that's going to migrate to the aqueous layer, and then we can drain that off. Well, so phenol is going to be useful. So addressing the question in the chat, phenol, the benzene group, the benzene with an OH group, is good to know as a very weak acid. So it can only be deprotonated by very strong bases. And P-cresol just looks a lot like phenol, and so that's where I'm getting that from. In general, phenol is good to know. Yeah, just you never know when it might come in handy. So okay, so we've gotten rid of we've drained out the benzoic acid in the form of benzoate. Now we've got 3 molecules in the organic layer. So we can address P-cresol next. Now it is a very weak acid that we can remove into the aqueous layer by deprotonating it with a strong base. So we can use something like NaOH. It then moves to the aqueous layer, and then we can drain that out. Now, the last thing we can do is the last thing we need to deal with is the aniline. Since aniline is a base, we can add a strong acid like HCl to protonate it. Okay. The diagram is slightly incorrect, so the P-cresol is gone. Ignore it; it's not there. All we have is the naphthalene and the aniline. So we protonate the aniline. That the aniline moves, is positively charged. It moves to the aqueous layer. We drain that out, and now we have a pure organic layer with just naphthalene. So are there any questions about that demo and how we went about it step by step? Okay, I don't see any questions. How do you choose which drain first? The order doesn't really matter because each thing is responsive to a different reagent. As far as the MCAT is concerned, I don't think you really have to worry about it. The real important thing is you don't want to add something that reacts with 2 or more of the molecules at a time. You want to try to get only one at a time, which is why we did a weak base and then a strong base. If we did a strong base first, so let me back that up a little bit actually, because if we did a strong base first, that would take out both. If we did a strong base first, that would take out both the benzoic acid and the P-cresol, which we could deal with, but it's easier to use a weak base first because then you can easily get rid of the benzoic acid first. Yes, you will get the slides after the session. Good question. I'm not expecting you all to write this down. Yep. Okay, so let's do a question. Shown to the right is the chemical structure of the molecule MCAT 101. Don't blame me, I didn't name it. Which of the following functional groups may be manipulated for the extraction of MCAT 101 into the aqueous layer? A, B, C, or D. So note that it's sitting in the organic layer right now. And that makes sense because we've got so much non-polar stuff going on with the benzene and the aliphatic carbons. So go ahead and throw your answers in the chat. Okay, good. I'm seeing a lot of C's, and C is indeed the correct answer. So A and D are non-polar and non-reactive and non-acidic or basic. So it's going to be those two are out. Amides are too weak to act as acids or bases in this case, and so we are left with the carboxylic acid group, which, if you deprotonate it, will end up in. So if the group were COOH, so that it were neutral, that would be in the organic layer. In this diagram, it's deprotonated, so that would be in the aqueous layer. Does that make sense to everybody? Okay, say yes if it makes sense.
Yeah.
Okay. Okay, good. Moving on. So, all right, so that is the end of the extraction section. So the idea is you don't need to be able to necessarily know how to do a complex extraction problem from scratch. That's not what they're expecting from you. But being able to identify when it's being used and then what strategies they might use in an experiment to isolate different molecules, that's what's going to really serve you if something like this comes up on the exam. Okay, so before we move on to distillation, are there any questions about extraction? And if you don't have any questions, just say no questions. Okay, excellent. If you think of a question, we can always come back. So now on to distillation. So distillation is, it's the relative, the basic overview of distillation is centered around boiling point. So different liquids have different boiling points, and distillation allows us to separate liquids based on their boiling points under various circumstances. So the basic premise is a heat source vaporizes the mixture. First, the liquid with the lower boiling point. It encounters a cooling segment, and then it condenses and drifts down into the receiving flask. Once the first liquid is fully vaporized and then condensed, the liquids are now separated. So simple distillation takes this idea at its most basic, based on the diagram we just looked at. We can separate liquids with boiling points that have a difference of at least 30 degrees Celsius. So that way we have enough time to finish condensing one liquid before the other one starts to vaporize. So for example, methanol, which boils at 65 degrees Celsius, and water, which boils at 100 degrees Celsius. So an example, we'd have a mixture of water and methanol. We would first boil off we'd heat it up. We'd first boil off the methanol, and then we'd boil off the water, and there should be nothing left. So this blue in the right side doesn't exist. I assume that this diagram makes sense overall to you guys. Okay, so fractional distillation. Now, it's a little bit more precise. You don't really have to know how this works. All you really need to know is that it's used to separate liquids that have boiling points that are less than 30 degrees Celsius apart. So this fractionating column is the key to that. You're essentially able to be more meticulous about your separation. So for example, isopropanol, which boils at 82.5 degrees Celsius, and water, which boils at 100 degrees Celsius. That difference is only 17.5 degrees, therefore you'd need to use fractional distillation. Vacuum distillation. Okay, so reducing the atmospheric pressure actually reduces the boiling point of a liquid, which is why water boils at a lower temperature in Colorado, for example, or any higher elevation. than at sea level. So for example, it would help us boil liquids that have a very high boiling point, and because it would lower their boiling point. And what's the key about this is that when you're heating a liquid with a very high boiling point, over 150 degrees Celsius, you actually run the risk of decomposing the one or more of the species that you're studying. And you don't want to decompose them, you only want to separate them. So if you lower the boiling point of all the species, you don't have the risk of an excessively high temperature decomposing those molecules. So if you were trying to separate decanol, which boils at 230 degrees Celsius, and dibutyl ether, which boils at 100, like this bar is in the way, so 141 degrees Celsius. They have very high boiling points, so you'd want to use vacuum distillation to be able to isolate them more effectively. Now, there are these things called boiling chips or boiling stones, which I refer to as the almighty boiling chips or boiling stone, because they just come up at the most random times on the MCAT, and they'll ask you why they use boiling chips for whatever reason. And so the basic idea is you're allowing it to boil more evenly, and it provides nucleation sites for vapor bubbles to form. And if there are no such sites, the liquid can, if it's jostled, can undergo violent flash boiling, which can be dangerous and just not a fun time. And so boiling chips or boiling stone will provide these sites. And so that can be useful. Okay, so before we move on to Ashley's segment, let's kind of recap. Are there any other questions? Are there any questions about either extraction or distillation? And if you have no questions, just say no questions. Okay, 2 people have no questions. Anybody else? Okay, cool. So with that, I'm going to turn it over to Ashley, and Ashley, you can just tell me when to change the slides as you need to.
Okay, sounds good.
Yeah. Okay, I'm going to mute myself.
All right, I guess you can change it now.
Okay.
All right, thank you. So starting off with thin layer chromatography, the goal of this process is to separate compounds based on differences in polarity. The main purpose of TLC is for identification purposes, not purification. So the setup of TLC is shown to the right. And you can see the mobile phase, which is usually a non-polar solvent. So for example, hexanes. And you also have the TLC plate, which is the polar stationary phase and is usually a silica gel coated paper. Next slide, please. So usually a very minuscule amount of a compound is spotted onto the TLC plate, and the non-polar solvents / mobile phase will travel up the plate via capillary action. So it will move the compound along the plate with it. And the speed of which the compound moves up the plate depends on its polarity. So because the stationary phase is polar, if the compound is also polar, it will spend a longer time interacting with the stationary phase. So it will travel more slowly up the plate because it is attracted to the TLC plate. So it would actually look like this yellow dot on the plate. Meanwhile, nonpolar compounds will interact with the nonpolar solvent more and will travel up the TLC plate more easily with the mobile phase. Next slide, please. So the MCAT will most likely ask you questions involving calculating the RF value. So what is the RF value? Basically, RF stands for retention factor, which is equal to the distance traveled by one component divided by the distance traveled by the solvent. So because the RF is a ratio and the numerator is always going to be smaller than the denominator, the RF value will never be greater than 1. If it is, then you've probably made a mistake. And it will always be positive because the distance can never be negative. So the greater a compound's RF value, the more nonpolar the compound is. Why? Because, as mentioned, nonpolar compounds will travel up the plate farther. So the numerator will be larger and so will the RF value. So here's a mnemonic that you can use to remember these rules. So polar is lower and slower, meaning that polar compounds will be lower on the TLC plate because they travel slower. So let's calculate the RF values of this example to the right. So the solvent line represents the distance the solvent travels, which is 50 millimeters, as I noted here, and the green compound is spotted on the starting line. And after being developed, it has been separated into compounds 1 and 2. So compound 1 in yellow has traveled farther, meaning that it is more nonpolar, and the distance it has traveled is 30 millimeters. Compound 2 in blue traveled a smaller distance, 20 millimeters, because it is polar. So to measure the RF value of compound 1, we take the distance it traveled up the plate, 30 millimeters, and divide it by the distance the solvent traveled, 50 millimeters, and we get 0.6. So the same thing goes with the RF value for compound 2. The blue dot traveled only 20 millimeters, so divide that by 50 millimeters, and you get 0.4. So the RF value of compound 2 is lower than compound 1. And by comparing these two values, we can conclude that compound 1 is more nonpolar. Does that make sense for everyone?
Yes.
Okay, great. So
Yeah.
next slide, please. Oh, that's great. Okay, so I have a question for you guys. You can type your answer out in the chat. All right, so for those of you who have answered, do you guys want to explain like how you got that answer, or should I do it? Okay, I'll just go ahead. So to answer this question that's asking about the greatest separation between compounds A and B, yeah, you're just looking at the difference. So we can use the RF values for both to get an idea of how far the two compounds traveled up the plate. So a greater difference of the RF values for both compounds would mean that that the distance they traveled up the plate is very different from each other. So B is the greatest difference. Does anyone have a question about that? Okay, next slide, please. This is just my explanation of it. All right, so I have another question for you guys as well. So yeah, you run a TLC plate with decane, acetic acid, and hexanol. Predict the order of the RF values for each compound starting from smallest to largest. So type out what you guys think the order will be starting with the smallest RF value. Okay, so we are basically ranking these compounds in order of polarity. So from most polar to non-polar. And the compound with the smallest RF value will be the most polar, which is acetic acid, since it's more polar than hexanol. And following that would be hexanol. So it would be, yeah, 2, 3, 1. Okay, next slide, please. All right, so we're done with TLC. That's pretty much all there is to it. So we'll just continue on with
Can
column
you give me a glass of
chromatography.
water, please? Please.
So Anna, I think you're unmuted. Yeah. Could you please mute yourself? Thank you so much. Okay, so the goal of column chromatography is to separate compounds in a mixture. So unlike TLC, the main purpose of this is for purification purposes, not identification. So you are starting off with a glass column that's packed with silica gel and saturated with an organic solvent. You then add the mixture to the top of the column where it will be separated as it travels down the column. So there are two phases in column chromatography, the polar stationary phase and the polar stationary phase, which typically includes silica gel, and the non-polar mobile phase, which usually includes the organic solvent. So the compound that exits the column first will be the most nonpolar. This is similar to TLC. The most nonpolar compound travels faster and farther. So as we can see in the drawing to the right, the more polar component is slower. So it will leave the column last because it is interacting with the polar stationary phase. So compounds exit the column in order of polarity. So from nonpolar to most polar. Like I said before, what did I say before? The mnemonic polar is lower and slower. Next slide, please. This is an example that pretty much sums up talking about. You have this mixture that contains compounds A and B. This mixture is then added to the top of the column so that the compounds can be separated. And you are left with two lines, one red and one blue. So I'll show you my thought process when I'm deciding which compound belongs to which layer. Again, using the mnemonic, polar is slower. I know that the blue line will correspond to the polar compound because it traveled slower. So that would be compound B because it contains a carboxylic acid functional group. Therefore, the red line would be compound A because it is nonpolar. You can also think of it in terms of how the compounds interact with the stationary phase. If you can remember that in column chromatography, the stationary phase is polar, then the polar compound will interact with this stationary phase. And because it's spending so much time interacting with this stationary phase, it will travel slower. Does anyone have any questions?
No.
Okay, great. So next slide, please. All right, I have a question for you guys. Once you're done, you can type your answer in the chat. All right, so everyone seems to be on the right track. So we can approach this question by identifying which compound is the most nonpolar and which is the most polar. So if you remember the mnemonic, polar is slower, we can see which compound would elute from the column last. So compound C, the most nonpolar, so that's going to elute first. Then compound B is the most polar because of the OH group, so that will elute first. So the order would be C, A, and then B. Does anyone have any questions? Okay. Next slide, please. Yeah, so that's just an explanation of the question. You can look it over after we send you guys the slides. All right, so that was it for column chromatography, and we're now moving on to our second to last technique. We have high performance liquid chromatography. So the goal of this technique is to separate compounds based on their affinities for either the stationary or the mobile phase. So this technique actually has a higher efficiency and speed than column chromatography. So in cases where that's needed, HPLC will be used. So below is a picture of what HPLC looks like. So a mixture will enter in the injector and will be separated in the HPLC column. The column contains the stationary phase. As the components exit the column and approach the detector, a chromatogram will be formed. The individual components are then collected in separate flasks. And in case you can't read my handwriting, I said HPLC column contains stationary phase where separation occurs. Next slide, please. So important to keep in mind is that there are two types of HPLC, normal and reverse. The MCAT will tell you if they're referring to normal or reverse HPLC. So normal HPLC follows the same rules as TLC and column photography. So the mnemonic polar is slower applies to this because the stationary phase is polar. Reverse HPLC follows the reverse rules. So you would have to think of the mnemonic backwards. In this case, polar would be faster. It's easy to distinguish between the two. You just have to remember what is eluted first. So for normal HPLC, nonpolar compounds are eluted first because it follows the mnemonic, and reverse would be the opposite as the name entails. All right, next slide, please. Okay, another question for you guys. Okay, so yeah, Quan is right. I wrote this question incorrectly. It's supposed to say reverse phase, not reverse HPLC. Okay, so I'll just explain my reasoning for this question. So keep in mind that this is reverse phase HPLC. We're going to have to reverse the mnemonic. So polar would be faster. This question uses a chromatogram where the retention time is on the x-axis and intensity is on the y. So compound A is more polar than compound B, and by the reverse HPLC rules will be eluted first. So it will correspond to Y. And compound B is more nonpolar, so it will correspond to peak X. Yeah, so this is my explanation for it. If you want, you guys can take a few seconds to just look over it. I know that reverse and normal can be a bit confusing. It just takes practice, really, and just remembering the mnemonics. Okay, I think we can go to the next slide, please. All right, so finally we are left with gas chromatography. The goal of this technique is to separate mixtures based on differences in volatility. This technique is primarily used for purification. There are two phases, the mobile phase and the stationary liquid phase. So you have to remember that the more volatile compound will be eluted first because it spends less time dissolved in the stationary liquid phase. Inversely, the less volatile component will spend more time dissolved in the stationary liquid phase and will be eluted last. Next slide, please. All right, so below is a picture of what gas chromatography looks like. The mixture is vaporized and carried along this stream of inert gas, usually helium, which is the mobile phase. The mixture then travels to the column coated with the liquid absorbent, which is the stationary phase. So each component interacts differently with the absorbent depending on volatility. Like I said, the more volatile compounds will be detected first because it spends less time dissolved in the liquid stationary phase. Next slide, please. Before we get into this question, does anyone have a question or confusions? All right, I guess you guys can answer the question. Not yet. How do we know which one is more volatile? Okay, so I guess we haven't really covered this, but based on the characteristics of the compound, you can determine if you can sort of rank compounds based on their boiling point, and that will give you an indication of how volatile they are. So I'll give a more detailed explanation after this question. So in gas chromatography, polarity isn't really the focus of it. It's more of volatility. So the stationary phase is liquid and the mobile phase is gas. The only thing you really have to, I guess, remember is that less volatile compounds will spend more time dissolved in the stationary liquid phase. So the main thing that you want to take away from gas chromatography is that the more volatile compounds will be detected first. Yeah. No, polarity doesn't really matter for stationary phase in this case, just in gas chromatography. All right, so do you guys want to give this last question a go, or should I just explain it to you guys? Because I know we haven't really okay. Yeah. So the way you would want to answer this question is by identifying which compound is the most volatile and associating that with peak X. So since, like I said, volatile compounds are detected first. So compound C would be our most volatile compound because it only contains London dispersion forces and is branched. So that makes the compound very weak and volatile. And B is our answer. Compound A, on the other hand, is the least volatile because it has that OH group. So because it has that like hydrogen bond, then it makes the compound more stable and less volatile. Does that make sense? how could I clarify it better for you guys? I guess just remembering that boiling point. So compound C has the lowest boiling point than all three, which is why it is the most volatile. Yes, volatile. I'm so sorry. I should have defined what volatile meant. So volatile means that it's ready to be vaporized because the bonds in the compound are very weak. Yes. So what makes a compound weak and volatile is the lack of polar groups, so like hydrogen bonds, and the compound being branched. So that's why C is more volatile than B. Based on structures, so the longer the chain of carbons, the higher the boiling point. And the more branched the compound is, the lower the boiling point. If you guys want, yeah, I'll probably edit the slide and make some rules about that and send it out to you guys, but I'll still try to have the slides sent out tonight. Yeah. Okay, so that was all the slides that I had for you guys. I guess Nita, you could go to the, I guess like the reminder slide. Yeah.
Okay, yeah, so just a brief housekeeping stuff. So we've got a GoFundMe. So this is all being run by volunteers, and GoFundMe helps to pay for some of our costs related to advertising and outreach, etc. We also have a Facebook group. You can access either of those via the QR codes that are on the screen. We can also send you the original links if you'd like to go about it that way. Email us at mcat101questions@gmail.com with any questions that you have, or any feedback or concerns or comments or anything like that. We're always open to feedback, whether it's positive or negative, and other ways that we can better make this content for you guys. And we will have a spectroscopy session for NMR, IR, etc. coming soon, because that's been pretty requested. Anything else you want to add, Sim or Ashley?
You got it. That was
okay.
Yeah, I don't have any additions.
Yep, you're good.
Okay, all right. Any questions from other sources? Okay, so it's a new question. So we can, I mean, you can ask us about other questions from other sources for sure. If you on an individual basis. I don't know whether we can actually present stuff because of like legality and copyright and stuff. Yeah, we will have more organic chem sessions. There is a survey where we're taking requests for like topics, like subtopics that you all want to go over. We'll send that out. We'll send that link out too. And yes, we will definitely be going over more organic chemistry concepts. All right. Any other questions? Okay, good. Well, we're glad that this was helpful. That's what we're going for. So if there's nothing else, then I'm gonna end the recording here. And